The next thing we're going to look at in this section is transforms of integrals. In particular, we're going to define the operation of convolution. Let's suppose that we have two functions f and g that are piecewise continuous on the interval from 0 to infinity. Then the convolution of f and g, which is denoted as f star g, is equal to the integral from 0 to t of f of tau times g minus tau d tau. Okay? So this is the definition of convolution of f and g. A couple important things. So first of all, notice that the integration is done with respect to the variable tau, and the definite integral has bounds from 0 to t. After finding the antiderivative of this function in terms of tau, we'd evaluate it at t and then also at 0. So ultimately what this will end up producing is a function of t. So keep in mind that when we're talking about the convolution, f star g, a lot of times we won't show the variable dependence, but f star g, the convolution of the two, is going to be a function of the t variable. Okay? And we're about to find out that convolution has a lot of nice properties, but let's start by finding an example of a convolution. So this is going to be example 3. Let's see if we can find the convolution. So for 3 part A, we're asked to find, or evaluate perhaps, the convolution of the function e of t with the function sine of t. Okay. So let me just kind of write down that definition again. If we have f convoluted with g, this is the integral from 0 to t of f of tau times g of t minus tau d tau. Okay. Here the function f is e to the t. The function g would be sine t. So this convolution, by definition, e to the t convoluted with the sine of t is going to be equal to the definite integral from 0 to t. This function we want to think of as a function of tau. So everywhere you see a t, put tau. So this is going to be e to the tau times g of t minus tau. So this is going to be times the sine of t minus tau, and then the integration is done d tau. Okay. We've seen this a bunch in Calc 2 and a few times in our class already, but when you're trying to integrate an exponential times a sine, we're going to need to use integration by parts. In particular, it's going to be integration by parts twice. So let's start off. I'm going to let the u be equal to the sine of t minus tau, and I'm going to let the dv be e to the tau d tau. Okay. So keep in mind, again, the integration is done with respect to tau. So when I differentiate u to find du, using our integration by parts formula, this differentiation needs to be done with respect to tau. So from the chain rule, the derivative of sine is cosine. So it's going to be the cosine of t minus tau. But don't forget, from the chain rule, we need to multiply by the derivative of the inside with respect to tau, and that's going to produce a factor of -1. So altogether, du is equal to the negative of the cosine of t minus tau, and don't forget, there should be a d tau then. And if we integrate to find v, the antiderivative of e to the t is simply, the antiderivative of e to the tau is simply e to the tau. So according to the integration by parts, it should be u times v. That's going to be e to the tau times the sine of t minus tau, evaluated from 0 to t, minus the integral from 0 to t of v du. That's going to be a negative e to the tau times the cosine of t minus tau d tau. So that's our integration by parts. We did it the first time. Let me kind of go ahead and delete this to clear some room. this is equal to, I'm going to evaluate this antiderivative. Everywhere we see tau, I'm going to put t. So it's going to be e to the t times the sine of t minus, remember, tau is getting replaced with t, minus, everywhere I say tau, I'm now going to put 0. This is going to be e to the 0 times the sine of t minus 0. And then notice here we have a negative and a negative. That'll make that a positive. The integral from 0 to t of e to the tau cosine of t minus tau d tau. This term here, t minus t is 0, and we know that the sine of 0 is 0. So that term is going to be 0. This leaves us with, this is going to be a negative sine of t for this first term, plus the integral from 0 to t e to the tau cosine of t minus tau d tau. And now we're going to do integration by parts again. Again, I'm just going to use the same variables u and v I did as last time. And be consistent here. You can change the variable names if you want to be proper about it. But the idea is, especially when you're doing integration by parts with exponentials times cosines, be consistent. The last time we let the u be the trig part. So once again, let u be the trig part. And we're going to let the dv be the exponential part, d tau. We take the derivative with respect to tau. The derivative of cosine is negative sine of t minus tau. But then once again from the chain rule, we need to multiply by the derivative of the inside. The derivative of t minus tau with respect to tau is going to give us a factor of -1. So just trying to simplify as we go. This ends up being the sine of t minus tau d tau. We integrate to find v. That's going to give us e to the tau. So this is going to be equal to, we have the negative of the sine of t, and then it's u times v, that's plus e to the tau cosine of t minus tau, evaluated from 0 to t, and then minus the integral from 0 to t of v du. V du is this, which is e to the tau, the sine of t minus tau d tau. And let's try to clean it up and simplify it as much as we can. This is equal to the negative sine of t plus, over here, we're going to evaluate tau at t. So it's going to give us an e to the t times the cosine of t minus t minus e to the 0 times the cosine of t minus 0 minus the integral from 0 to t of e to the tau sine of t minus tau d tau. This is equal to the negative of the sine of t. Here, this is going to be the cosine of 0, which is 1. So this is going to be e to the t times 1, which is e to the t. Here, e to the 0 is 1. This is going to be minus the cosine of t. And then we have this minus the integral from 0 to t, e to the tau, the sine of t minus tau d tau. And now what we realize is that this convolution, the thing we're looking for, this is cyclic. This is the thing we were trying to solve for in the original beginning. Okay, if you want to, let's call this w. Okay, so the quantity we're looking for, call it w. Then what we have is this equation here. So what we've shown is that w is equal to negative sine t plus e to the t minus the cosine of t And then minus, again, this is the convolution thing we're looking for. This is w. We can add w to both sides, so bring that common term to one side. And what that tells us is that 2 times w is equal to negative sine t plus e to the t minus the cosine of t. So to get the thing we want, all we need to do is divide the entire equation by 2. So let's go ahead and divide everything by 2. And so what we have is that w, which is equal to, this was our convolution, it was e to the t convoluted with sine t. This is equal to negative 1/2 sine t plus 1/2 e to the t minus 1/2 cosine of t. So we now have found the convolution of e to the t with sine t. For the second half of this problem, let's now go ahead and find the Laplace transform of this convolution. So for part B, we want to find the Laplace transform of e to the t convoluted with the sine of t. Okay. This is equal to, well, we just found what the convolution is equal to as a function of t. It's negative 1/2 sine t plus 1/2 e to the t minus 1/2 the cosine of t. And the Laplace transform is linear, so this is negative 1/2 times the Laplace transform of the sine of t plus 1/2 times the Laplace transform of e to the t minus 1/2 the Laplace transform of the cosine of t. Okay. This is going to be equal to negative 1/2. We know that the Laplace transform of the sine of t is 1 over s squared plus 1 plus 1/2 times the Laplace transform of e to the t is going to be 1 over s minus 1, and then minus 1/2 the Laplace transform of the cosine of t is s divided by s squared plus 1. So we end up with this, and I'm not going to go ahead and really work out the algebra for this, but I'll leave it up to you. It's just a simple exercise combining, getting common denominators and all of the like. But if you do that, what you will find out is that this is equal to 1 divided by s minus 1 times s squared plus 1. Okay. And this is very significant. And let me rewrite it. So this is the final answer. So this is what the Laplace transform of e to the t convoluted with the sine of t gives us. But if I write it like this, I can write this as 1 over s minus 1 times 1 over s squared plus 1, which is totally true. And what this leads us to is our very next important theorem, that if you recognize these, what is 1 divided by s minus 1? Well, 1 divided by s minus 1, that was simply the Laplace transform of e to the t. Times, what was this thing? Well, that's the Laplace transform of the sine of t. And this is one of the really cool properties as it pertains to convolution. So be aware. So one of the things I'm going to talk about in terms of Laplace transforms for a minute is that if you're trying to find the Laplace transform in general of some function f of t times some function g of t, okay, in general, this is not equal to, where we're taking this to be like the traditional product, old school multiplication of functions. This is not the Laplace transform of f times the Laplace transform of t. Okay. However, and this is our new theorem. This is theorem 7.42. It does turn out that with the kind of quote-unquote product as being convolution, that if you have the Laplace transform of the convolution of f with g, that does turn out to be the product of the Laplace transforms of f times the Laplace transform of g. Which typically we would call, f of s times g of s. So this is a really awesome property that a convolution satisfies in terms of the Laplace transform that general multiplication would not satisfy. One of the other properties before we move on to the next example is, and I'll let you show this, but convolution is commutative. This can be shown via a really easy u substitution in the definition of convolution. But convolution is commutative. What does that mean? Well, that means if you do f convoluted with g, you would get the same result as if you took g and convoluted it with f.